Our second chapter, Chapter 2, Protecting the Ozone Layer. As you can tell from the graphic, this is a 2012 picture, stratospheric ozone hole over Antarctica. See that purple and blue area showing where the ozone is at a minimum? On September 22nd in 2012, the hole reached a maximum area of 21.2 million square kilometers. The record high for the hole was 29.9 million square kilometers in 2000, which is actually a very good sign that it might be shrinking according to new statistical data. So as we begin exploring protecting the ozone and just thinking about the missing word there, the title of our chapter, Protecting the Ozone Layer. Why do we need to protect the ozone layer? What is its purpose? Isn't ozone hazardous to human health? And again, we'll explore where ozone is located, certainly matters in terms of what part of the atmosphere. And why is the ozone layer getting smaller? And what can we do, if anything, to help stop the depletion of our ozone layer? These are the topics we'll be discussing through our lessons in Chapter 2. We begin with a little saying called good up high but bad nearby. I know that good up high because the ozone in the upper atmosphere is screening us from any type of damaging solar radiation. So the stratosphere is the good up high part. So here we have a very important role for the ozone layer, forming a natural screen filtering us between the damaging solar radiation that the sun gives off in terms of UVA, UVB, and UVC radiation. But bad nearby, that's this component of our atmosphere. Ozone is a pollutant that forms in the presence of sunlight from other pollutants, specifically known as radicals, in our atmosphere. Of course, this is at the Earth's surface, known as the troposphere. If ozone is present, it is considered a pollutant. Up higher in our atmosphere, in the stratosphere, we see an ozone layer that serves as a very important role for our protection. At this point, I would like you to pause this lesson and go into the folders for the video clips called Ozone Layer Danger and Exploring the Ozone. They are less than 5-minute clips produced by NASA, but they do an excellent job at kind of staging the entire purpose and the entire lessons that we present in our ozone layer chapters. Again, pause the video, just take a moment to watch and enjoy these clips, getting the information set for our next lessons. Welcome back, and I'm glad you took the time to watch those opening videos. Scientists made a discovery that certain chemicals could make their way up into the upper atmosphere and begin destroying the ozone. And this was occurring in the 1970s where the research was happening. The most severe damage had been over the Antarctica. Not to say that the Antarctica is the most populated area, have any industry at all, but really it's thought because of the weather patterns and the jet streams that were bringing these chemicals into that particular area on Earth. And once they converged over the Antarctica area, they started to destroy the ozone layer. So it's documented damage in many other locations on Earth as well. I know there's an ozone hole that's being studied in the atmosphere over Australia as well. But the largest one that we've been researching is over Antarctica. And again, not because of population there, but because of weather patterns and the jet streams bringing or converging all of those pollutants in that direction. And so we begin this precautionary principle. We're stressing the wisdom of acting even in the absence of complete scientific evidence. Before any more adverse effects on human health, such as skin cancers or genetic mutations, or the environment become significant or irrevocable. We can't turn the clock back. If the pollutants are already up in the stratosphere, how are we supposed to go and get them back? So we have been noticing a significant improvement in what we call the ozone layer hole, the ozone hole, simply because we've been working on a precautionary principle. We have stopped putting the pollutants into the atmosphere that we know are causing damaging effects. Perhaps you've heard of the term chlorofluorocarbons. Chlorofluorocarbons, those are just the elements involved. And so chloro comes from the element chlorine. Fluoro, which I'm writing here, oops, I wanted to just go straight to the L. So let me try to erase that. Thank you for your patience. What we'll do here is just tell us a little bit about those elements that are in there. Chlorofluorocarbon are those elements contained in a pollutant where we have carbon as the central atom, and we start to see these molecules that contain fluorines and chlorines all attached back to that center carbon. This is a very well-known pollutant. Perhaps if you've heard of a refrigerant known as Freon, we used to use Freon in automobile refrigerating systems or air conditioning systems, and this, of course, once it's released into the ozone, would damage it. Radicals such as nitrous oxides or NO2s or NOs, these radicals, which we'll talk about a little bit further down, these are naturally occurring pollutants, and these freons or CFCs are synthetically man-made produced pollutants, and all of them have been working to damage the ozone. So what we're stressing here is we're using the wisdom of acting to prevent these from ever reaching the stratosphere, thus preventing the destruction of the ozone layer. So we have a big job in front of us in this chapter to talk about ozone and its chemistry and why is it important to us here on Earth. Well, let's begin with a talk about the ozone molecule. An ozone molecule is an allotrope of molecular oxygen. Allotrope just simply means a different form of the same element that we find in nature. So one form of oxygen is O2. This is naturally occurring molecule that we breathe in. O2, molecular oxygen. And ozone is an allotrope, just a different form of this particular element where it has 3 atoms of oxygen bonded together. And so we see with molecular oxygen, we would see this 2 bonded molecule. These are electron dots. Here's a picture of molecular oxygen, O2, double bonded, 1 oxygen atom to the other. But with this molecule known as ozone, we have 3 oxygen atoms bonded together, and we actually have a double bond in one direction and a single bond in the other. And we'll discuss this more at length, called a resonance structure. But here is just getting a general picture of how the 2 allotropes of oxygen differ from each other. Even though they're the same element, they're both forms of oxygen, they are very different chemicals, very different physical and chemical properties from one another. Ozone literally means to smell. It has a very distinct odor. It's very difficult to describe what ozone smells like, but it's clearly a unique smell. When ozone forms, it needs energy to do so. Energy in the form of sunlight, perhaps, with the radiation coming from the sun. This is known as activation energy, some sort of energy that institutes the change in molecular oxygen forming ozone. So our balanced chemical equation would say if molecular oxygen, remember this is reading it as we have 3 diatomic molecules. That's what 3O2 is representing, 3 molecules of O2. And when it's zapped with electricity or some sort of activation energy, for instance from the sun is emitting this UV radiation, and when it's hit with these molecules, these bonds will break and new bonds will form. And what we end up creating are 2 units of ozone. So here we would have just a different rearrangement here of those 6 oxygen atoms over here, the 1, 2, 3, 4, 5, 6 oxygen atoms double bonded here to make 3 O2 molecules. When this is hit with energy, these bonds break, the atoms rearrange, and they form 2 ozone molecules. So energy must be absorbed, a very endothermic reaction for this to occur. An electric spark or lightning can act as the activation energy. Ozone, we mentioned, is an allotropic form of oxygen. And here's our definition for an allotrope. Two or more forms of the same element that just differ in their chemical properties. That got overwritten. The chemical properties are different just because they've arranged their atoms in a different bonding order. Oxygen, O2, is called a molecule of oxygen. O3 of oxygen is known as ozone. Another example of a allotrope, which comes from the element carbon, different ways that we find carbon in nature. We see it as graphite, which is like a pencil lead. We see it as a diamond. They're both forms of carbon. And a Buckminster fullerene is also known as carbon. Just a different arrangement. This arrangement for a Buckminster fullerene is like a soccer ball. So an allotrope is simply different ways to arrange the same elements. Here's some just general facts about ozone as we begin our studies. Ozone is far more chemically reactive than molecular oxygen. So molecular oxygen must be more stable. Ozone is more reactive. We use ozone to kill microorganisms in water. For instance, in water filtration plants, you'll see ozone bubbling in. Some people will even use ozone in their hot tubs or in their pools instead of using chlorine or bromine bases. It's used to bleach paper pulp and fabrics. It can form naturally and as a result of human activities. So ozone forming naturally from a source of radiation such as from the sun or lightning, or as a result of human activities. If we start releasing pollutants into the air, we might produce ozone from molecular oxygen. It's rare in the troposphere, approximately 20 to 100 parts per billion. And published by the EPA, our acceptable level of ozone is 75 parts per billion for an 8-hour average. Would still be, this is just air quality index published by the Environmental Protection Agency, setting a standard of no more than 75 parts per billion to be exposed to that in an 8-hour average. So rare in the troposphere, but common in the stratosphere. Let's kind of dive into that. We'll just get a handle on where the layers of the atmosphere are located. So here we are at sea level. And at sea level, and approximately 15 kilometers high, we have what's known as the troposphere. See this word here? Troposphere. Now in miles, it's 0 to approximately 9.3 miles up. We have this troposphere. This is where we live from sea level. Denver, which is a mile high. Here we're at the top of Mount Everest. This is where the airplanes fly. And then at about 15 kilometers high, the air is quite thin. We have a second layer from 15 kilometers up to 50 kilometers. This entire layer here is known as the stratosphere. And at 50 kilometers and above, we have the mesosphere. The stratosphere is where we see the most abundant naturally occurring ozone form. This is what we refer to as the ozone layer. So tops of very intense thunderclouds are in the stratosphere. Weather balloons fly in the stratosphere. Satellites fly in the stratosphere, and so forth. So here we are at the Earth's surface in the troposphere, and up higher is the stratosphere. The most abundant naturally occurring ozone is in the stratosphere. And if you find ozone down here in the troposphere, it's considered to be a pollutant. Remember our saying? Good up high, bad down low. Good up high, bad nearby. With this particular graph, what we're looking at here, again, in kilometers, from 0 to 15 kilometers is the troposphere. And then from 15 kilometers up, we have the stratosphere to approximately 50 kilometers, and then above is the mesosphere. The ozone layer exists right after the troposphere at the start of the stratosphere. So as altitude increases, we have a naturally occurring ozone layer where we see the greatest abundance of ozone. Whoops. So the regions of the atmosphere, have you ever been in a plane landing in Denver, Colorado? You notice that the Denver, Colorado is a mile high. The air is thinner. You see the thrust forward as the plane uses more energy to stop. That there are fewer air molecules at that height, reducing the amount of friction. So a greater amount of energy is needed to stop the plane. So the air is thinner, less dense, fewer molecules hitting you in Denver, Colorado than if you were landing at sea level, where there's more molecules, more air pressure pushing against the plane, and it would actually stop sooner. So it takes longer to cook an egg in Denver than it does in New Orleans, because New Orleans is technically below sea level and Denver is a mile high above sea level. You would have more air molecules in the sea level area, fewer air molecules up high. So less air pressure at higher altitudes. When water boils, it's boiling to reach that vapor pressure, so of course it's going to boil at a lower temperature in Denver, Colorado, thus needing a longer time to cook. So all of this is just reminding us that the greatest number of molecules occurs at sea level, and as we begin rising in altitude, the air thins out. There are not as many molecules creating air pressure, and you'll notice that the pressure is dropping as you go higher and higher in altitude. So this ozone region, in terms of concentration, in the troposphere, we see a very low amount of ozone, naturally occurring ozone. In the stratosphere, we see a very maximum amount of naturally occurring ozone, and then again it depletes as we begin to climb in altitude. This is what's known as the ozone layer, where the naturally occurring ozone is most abundant. So good up high, bad nearby. If at sea level and approximately a mile high in Denver, Colorado or so forth, this is where people live on the Earth's surface, you start to see an increase of the ozone. We start to know that it's a pollutant. It is actually harmful to our health here, but very beneficial to our health here. So let's check for understanding. And these are processing questions that allow you to make sure that we've accomplished the learning goal from Lesson 1 before we move into Lesson 2. Can you describe what the ozone layer is? Can you describe what range of ozone molecules per billion molecules of all types are found in the stratosphere? And what is the maximum number of ozone molecules per billion and all atoms found in the ambient air, meeting the EPA limit for an 8-hour period? These were in previous slides talking about air quality index. So those two last bullets come from this reflection. So the air quality index set it for 75 parts per billion over an 8-hour period, and it's approximately in the troposphere, ozone is contributing about 20 to 100 parts per billion of the overall number of molecules in the atmosphere. So with that particular slide, we're just reflecting on those particular numbers set out by AQI, Air Quality Index, which is published by the EPA. That's the Environmental Protection Agency. And when you feel comfortable with the lesson so far, let's continue. I'm going to pause the video here, and when you're ready, start your next lesson.